Okay, good evening, everybody, or good afternoon, since this is actually going to be played on Thursday. This is Mr. Steele. I'm coming to you not so live via video, continuing our lecture from yesterday where we began talking about first sigma notation and then finding the area under the curve. So where I wanted to begin is I wanted to begin by just going over and talking through 5A. We already did this one together at the board, and we kind of started on 5B, but I'll start by just kind of talking about 5A a little bit to get the ideas back into your head. Then we'll move on, we'll finish 5B and actually go through everything there. We'll also take care of 5C, so we'll do that area problem 3 different ways there. Then we'll move on and we'll start transforming this into finding the exact area under the curve using all the tools of calculus and summation that we already have, and then doing the same thing with the slightly modified version of what we have. So again, like this will be continuing in that packet that I gave you yesterday, so just try to follow along. I'll also post this online, or I'll try to when I'm done, so that you have access to it in case it went a little fast, because I'm not sure exactly how it's going to go. I want to make sure it doesn't take longer than the actual period. Okay, so getting started on what we have, I'm going to begin by going over the first example from 5A. And what we were trying to do is we were trying to actually find the area under the curve for somewhat ambiguous reasons. Like, I didn't give you a very good answer of why we were doing it. It was just something we're doing, and it will lead us forward with antiderivatives and everything else in calculus. So what we did was we were told to use 6 rectangles to approximate the area of this guy. And so our idea was basically this. We went and we wanted to figure out how to make an equal number, or each of those rectangles have an equal width, and then we were going to actually draw in those rectangles, and we're going to use what was called the right endpoint rectangle area method. So what that looks like in our picture over here is that we were basically going to say, okay, our rectangles are each going to have a width of 1/2. The reason for that is because the spread of our interval, like the distance between the two endpoints, on 0, 3 is just 3, and then there are going to be 6 rectangles. So 3 divided by 6 is 1/2. So each of our rectangles will have a width of 1/2. Going over to our picture then, we're going to have rectangles about here. I apologize, this is still a little new for me getting used to drawing this. There's going to be one rectangle's width, there's another, there's another, there's another, there's another, there's another. That would give us 1, 2, 3, 4, 5, 6 rectangles. So those would be our widths. As far as the heights, well, the height's going to depend on the actual value of the function, because that's what we're trying to approximate. So we'd take the height there, and that would give us a height for one rectangle. We'd do the same thing right there, get a second rectangle. Do the same thing right here, get a third one, and so on and so forth. And all the way up there at the top. And there we go. That's going to be our approximation. What we're going to do is to approximate the area, we're going to add up the areas of each of these individual rectangles. Number 1, 2, 3, 4, 5, and 6. And now, of course, to do that, though, we do have to figure out what is that height. And what we discovered, or what we talked about, was the fact that the height depends on the rectangle, or it depends on the value of the function. So basically, it's going to be the value of f of x, in this case x squared, evaluated at some partition values like c sub I. And those 6 values, one for each rectangle, are going to be determined just by what we see. Like, basically we can look and say, okay, well, if the width is a half, we'll have one rectangle that's 1 at 1/2, one at 1, one at 3/2, 2, 5/2, and 3. And each one of those will be a value where we can evaluate the function itself at that level, and that will tell us the height of this rectangle. I mean, for example, if we just look at the 6th rectangle over here, the height is clearly 9. Like, we can tell that based on the picture right here. And obviously that's going to be the value of 3 squared. Our last c sub I, c sub 6 if you will, it's the 6th one of our partition values. We plug it into the function, which means we square it, we end up getting 9. So when we do that, as far as what we're actually looking at, kind of the formula that we've got at work here is this one. Our approximate area using rectangles is going to be equal to the sum from 1 to n being the number of rectangles that we need, of f of c sub I times delta x sub I. That's going to be the height of the rectangle times the width of the rectangles. And then we're just going to add them all up. Well, when we make this more specific then, we're going from 1 to 6, as I said, because there's 6 rectangles. Then we're going to square all those individual values, because f of c sub I is just x squared, which means we're going to square c sub I. That's where this comes from. And then of course multiplying times the width, that's just 1/2 every single time. So now as far as doing the summation, since it's just 6 little rectangles, 6 little things to add up, all I did was I factored out 1/2, factored out the width since that was a constant, it's always going to be 0.5, and then I went through and I just evaluated what each of those height values, or the function value where we evaluate the height, will end up being. In this case it was 1/2 squared, 1 squared, 3/2 squared, 2 squared, 5/2 squared, and 3 squared. Each of those was an individual value. Sigma notation tells us we're going to add those guys up. So we're going to add the individual areas of each 6 rectangles, and then we're going to simplify. And when we do that, we found out that the area underneath the curve was 11 3/8. Now, this is kind of a shoddy picture. Not that I want to badmouth my nice little drawing here, but I do want to show you that there's this really cool Java applet that I found online yesterday that actually lets us see this another way, or at least it doesn't let us see it, it's a different way, it's the same way, it's just really neatly done. So I just want to pull that up really quickly and take a quick look at it. And so again, what we're going to do is let's just see, like, did we actually do this correctly? Because I tend to trust random calculus websites on the internet more than I trust myself, especially when it comes to calculations. So what we want to do is we're going to get the area under some sort of parabola. Our function is x squared. We are starting our x value at 0, and we're ending at 3. We want to use 6 intervals, and in this case, we're using the right endpoints. So notice it automatically switched over, and you can kind of see in the picture what's happening. As far as our window, well, to get it to match my beautiful picture over here, I'm going to go from 0 to 4 to give ourselves a little bit of room. I'm going to go from 0 to 9, then I'm going to set limits. And there we go, there's our picture. So this picture is approximating the same thing that we have over here. Windows 7. There's our picture. Okay, so we're looking at, notice there's 1, 2, 3, 4, 5, 6 rectangles. So those are our 6. And now we want to actually calculate the area of them. And what it does up here is it tells us what our delta x is. That's our delta x sub I. That's our width. And then the blue area is the combined areas of all our rectangles. Notice it says our blue area is 11.375 units. That's exactly the same thing as 11 3/8. You can check your calculator if you don't trust me. And so there we go. Random applet that I pulled up out of nowhere confirms what we saw. And of course the process should somewhat make sense because we really are just working with rectangles, and rectangles are fairly nice to work with. And so there is just kind of a quick review of part 5a, our first step into finding the area under a curve. Now, before we go on to it though and move forward, remember that one of our problems here was that this thing obviously couldn't be the area under the curve because there's all this extra space and all these little things. There's superfluous rectangle. And in fact, this is an overestimation. I know I used the very technical terms too big yesterday, but it's a nice term to say that, well, no, this can't be the area under the curve. This is an overestimation. So what we've really found is like an upper bound. 11 3/8. Let's see if I can do this correctly. 11 3/8 is bigger, than the actual area. But we don't know much else. Like, we don't know what the exact area is, and we don't know exactly what a lower bound is going to be. So what we need to do is calculate the area in a different way and see if we can start to compare it and start to kind of narrow in on what our actual answer is going to be. Okay, so next, where we're moving on is we've just found the area under the curve here. We've overestimated it a little bit by using the right endpoint rectangles. So now we're going to move on and do the next thing. We started this a little bit in class, but I'll go through it from the beginning since I know it was getting close to the bell. And once again, we want to use 6 rectangles to approximate the area of the region that's found underneath this curve, all down in here. And we want to do that this time using inscribed rectangles, or ones that use the left endpoint rectangle area method. So now the first thing I'm going to do is, before I even go over and start this, I'm just going to start by actually drawing out those rectangles. What I can kind of tell you is, we'll do it more, I'll talk about it a little bit more, but obviously the width's going to be the same because we're still using 6 rectangles and we're still on the interval 0 to 3. So I think you can probably anticipate that as well. So we'll have one at 1/2. We've already got one there, one here, one here, one here, and one here. So not perfect, but I'm not that good at drawing on this thing. So 1 rectangle, 2, 3, 4, 5, 6. So those are our 6. And now if we use the left endpoint, we won't be going up and over like that. We'll actually be using the points on the left. So our first rectangle is actually going to be, well, not considering my poor drawing skills, it's going to be like a trivial rectangle. It's going to be height 0. But that's okay. That still counts as a rectangle for our purposes, because obviously we're using the left endpoint to calculate the height. Our next rectangle, a little bit easier to see. Go up and over. Next rectangle, up and over. Next rectangle. Next one. And lastly, I know these are some of the squiggliest rectangles you might have ever seen, but there we go. We now have one, even though it's trivial, it's okay, 1, 2, 3, 4, 5, 6 rectangles to look at. And those are going to be the 6 that we actually use to calculate the area under this curve. And now, even before we do the calculation, we can kind of see what's happening here. As we've gone through, we've got our 6 rectangles, but you can see this time, instead of having a bunch of excess rectangles sitting up here over the edge of the curve, now we've got it all underneath. Like there's actually open areas that never get touched. Like my mouse is hopefully pointing to those areas. I mean, none is bigger than this guy. And so unfortunately, this one is going to be, instead of an overestimation, this one's going to be an underestimation. And we can tell that just right now based on the graph and the shape and our own sketching. So it's an underestimation, so this one's going to be too small. But again, that's going to be okay. We'll actually get a lower bound for the area under this curve, and so that'll at least give us some idea about the size of what's there. So again, just something to pay attention to and kind of help us with our intuition as we get started. Okay, now going to actually doing this problem. Let me change pen color so it stands out a little bit more. Let's keep the Franklin purple. Okay, so what we got? Well, our area formula, or our approximate area formula, is of course equal to that same thing. We're going to sum up all the rectangles, all n of them. In this case, n is going to be 6, but we'll save that for a second. We're going to sum it up by calculating the height of the rectangles by using the function values, and then multiply it times the width of each of those rectangles, which we can find as well. And so now each of these we need to get. So let's do that again really quickly. So delta x sub I, that's our width. It's going to be the width of each rectangle. And recall that the way we find that is we take the spread of the interval, so the distance between 0 and 3. In particular, that's 3 minus 0. Then we divide it by however many rectangles we need, which is 6. So once again, as we used in our picture, we're going to have rectangles of width 0.5, which is fine. Again, we're using 6 rectangles, same interval, that should make sense. Excuse me. Okay, the second part. We need the f of c sub I. So we need all of those individual heights that we're going to use for the rectangles. And now this isn't just one piece. We can't just like jump into our answer. Instead, we've actually got to think about first, what are those c sub I? Those values we're going to use to partition up our interval. And now when we look at it, the heights that we're using to actually calculate this, the first height is at the left endpoint. Notice that this is, in fact, the left, or the L RAM. We're using the left endpoints. So our first endpoint, the left endpoint right there, is actually just 0. So one of our c sub i's is going to be 0. And then from there, they're going to be familiar faces. The next one will be 1/2. The next one will be 1, 3/2, 2, and 5/2. And that will give us our 1, 2, 3, 4, 5, 6 different rectangles. So those will be the values at which we evaluate the height of all 6 rectangles. Now in order to find f of c sub I, like the actual individual heights, that's going to mean we're going to use the function itself. So once again, our function is x squared, so we're going to square c sub I. And then we'll calculate each of those individual values. So now going to our actual calculation, so the area underneath this curve, so it's not really the area under the curve, it's just an approximation. I'm using left endpoints. That area is going to be the sum from 1 to 6, so 6 rectangles, we're going with all 6 of them, of f of c sub I, so in particular we said that's c sub I squared, times delta x sub I, our width, which is just 1/2. And so once again, I can pull out that constant, that 1/2, and then go through and actually evaluate c sub I squared. So I'm just going to take each of these, I'll use a different color so we can see it a little better. I'm going to go up to my c sub I, and then I'm going to square them all. And then that will give us the values that we're going to evaluate in here. So 0 squared is 0. 1/2 squared is 1/4. 1 squared is just 1. 3/4, or 3/2 squared, anticipating my answer, is 9/4. 2 squared is 4. And 5/2 squared is 25/4. Once again, we need heights at 6 rectangles to evaluate them all. 1, 2, 3, 4, 5, 6. There are 6 heights. And then, of course, when we go to actually find the area, we just need to simplify and multiply everything out. And according to my calculations, I get 6 and 7/8 as my area. And so there we go. We found a number much lower. The last time, if memory serves, or this mouse serves, it says that our area was 11 3/8 if we used right endpoints, which gave us an overestimation. And of course, our one that keeps all the rectangles underneath the curve, well, it gives us a much smaller number. So assuming we did everything correctly, so if we get this over there, we now actually have a nice little thing to think about. Like, we know that 6 and 7/8 is going to be less than the exact area under the curve, and it's going to be less than 11 3/8 as well. So that's kind of our, just a statement we don't have. We aren't asked to do that, but it's something good to keep in mind. So whatever our final answer is, it should be between those two pieces. Just like last time, we can check it again really fast, just make sure we did this correctly. Launch presentation. Okay, so once again, for some reason it's not letting me keep my stuff here, so we're going to start 0 to 3. We're going to use x squared. We're going to use 6 intervals, specifically that's 6 rectangles. We're going to use this time, was it the left endpoints? It was the left endpoints. And then we're going to, smallest x value will be 0 to 4, 0 to 10, and there is our picture. So this is the picture that should be matching the one we have over here. When you look at it, you can see it does. There's our very, very short rectangle. Don't call them small, just short. Our height challenged rectangle. Then we've got our second, third, fourth, fifth, sixth. And there are 6 rectangles. It says our area should be 6.875. And in fact, that's the same thing as 6 and 7/8. So once again, we can feel good about ourselves and our ability to do this. So there we go. We've now found an approximation for the area of the curve using the left endpoints, otherwise known as inscribed rectangles. Hooray. Okay, so we've done an overestimation, we've done an underestimation. Obviously our next goal should be to get this better. We won't necessarily get to, well, we will get to exact in another problem. But for now, we want to just get it as close as possible to the right answer. We want to try to find something that still uses 6 rectangles. Like, we're still going to use 6, because that's our, that's our goal. We're trying to use that as our approximation for now. But we want to start making it better. And so obviously what we need to do is find a way to kind of shave off some of that excess rectangle and fill in some of that missing rectangle. So we want our missing area. So like right here, we've got all our extra little pieces. We need to shave that down as much as possible, and then we need to kind of fill in some of this if we want to get actually closer. And of course, if we find a way to do that, that answer should be somewhere between these two, because we've seen a huge overestimation and a significant underestimation. Okay, so to go through this, process is going to look very much the same. So we're using midpoints now. That's of course what Amram stands for. You can probably figure that out. Just like if it was BRAM, it would probably stand for Bigfoot. But M does in fact stand for the midpoint rectangle area method. So now what we're going to do is we're going to look for the same pieces. Like our formula, once again, it's going to be the same thing. It's going to be the sum of how, oops, that's a really crappy sigma. So we're going to go from 1 to n, in this case 6 because we have 6 rectangles, and we're going to multiply width times height, or length times height, however you want to think about it. That of course fits this pattern. So starting things off, we need both the width, which is right here, and we need the heights, which will come from here, or will be placed in there. For our width, again, nothing has actually changed. Like our rectangles are still going to be width 1/2 because we're still on the interval 0, 3, meaning that they're still 3 units apart. We're still using 6 rectangles. So in fact, the width does not change at all. Our height, though, that's where our significant change is going to come in, as our heights are going to be at different places. So of course that's going to be f of c sub I, which is easily just whatever those partition values are, we're just going to square them, and we'll find our values by using that since it's dependent on the function. But now the problem is finding those c sub I. is we've got to have them be the midpoints. So we have to look over here and figure out, okay, what are those midpoints going to be? And now, if this was a bigger problem, we'd have to actually probably find a formula for it. But in this case, with 6 rectangles, I think we can probably do it like normal. So here we go. Let's see if I can do this right. So we said the rectangles are going to be each 1/2 wide, or 0.5 wide. So I'll draw that in. That part is not going to change because same interval, same everything. Now for our rectangles though, we want to be at the midpoint between each of those pieces. So the midpoint between here and here, well, that's going to be right there. So our rectangle is going to be like that. The next one, the midpoint would be right here. So right there. Let's see if I can do this right. Do it a little better. There we go. Next midpoint, going halfway in between to be right there. So up and down. And that's probably annoying to watch someone try to draw with a shaky pen thingy on a televised lecture, but so it goes. I feel good about it sometimes. So there's our next one. Next piece, midpoint would be like right there. And then lastly, our last midpoint would be somewhere around there. That was a really straight line. I'm proud of myself. And there we go. 1, 2, 3, 4, 5, 6 rectangles. So once again, we've got 6 rectangles, and now we've used the midpoints. We use the value kind of in between here to calculate the height of our rectangles. Excuse me. Okay, so take a look at it for a second while I drink a little bit of water and kind of compare it in your head to what we've done before. Like, does it look like it's a better approximation, and why might that be? H2O. This presentation is brought to you by water. Actually, water would be less likely to sponsor something because water is free and doesn't have a marketing board. But maybe that'll be my next career, a water marketing board. Anyway, okay, so looking at it, hopefully what your conclusion would be, looking at my little picture or drawing it out for yourself, probably better. What you probably think is that obviously this is a better approximation. Instead of having tons and tons of space over above it, like we did up here, where there's all this extra little rectangle area, even color it in a little bit. Like instead of all that little extra area, like that's not there. We've got a little bit less, we've got a little bit over each time. But it's also not way under. Like we don't have huge chunks of space underneath it anymore. We've got a little bit of space each time. And hopefully what you can kind of see is if you imagine this little area, like say the area right here, looks like it might even fill in some of this area. Or this little extra area might fill in this one. So what you're probably thinking is that, this thing looks like it almost cancels everything out. Like it almost cancels, like the extra area cancels out with the missing area. And that's actually pretty cool, and that should match your intuition that, hey, this is getting us pretty close to it. So we can see from our picture we're getting close. We might be around that exact area, but now of course we want to find that exact value. What is the area when we approximate it with 6 rectangles calculated at the midpoints? So to do that, I think it's easiest just to look at our picture and think about what the C sub I are going to be. What is that place going to be each time where we evaluate the height? Let's think about this one. This is between 0 and 3, and each one's 1/2. So this is 0, and this is 1/2. The midpoint between those two is just halfway between them, which would be 1/4. So one of our C sub i's is going to be 1/4. Our next one, halfway between 1/2 and 1, is going to be 3/4. So there's our second one. Next piece, between 1 and 1.5, or alias 3/2, is going to be 5/4. So, what your mind's probably saying at this point is, boy, that sure looks like it might be some sort of pattern. So there we go, 3/4 and 2. Of course, that's going to be 7/4. Quarter between each time. Between 2 and 5/2 is going to be 9/4. And between 5/2 and 3 is going to be 17/4. Just kidding. Fooled you there. Bet some people actually wrote that down without even thinking. Of course, that one is going to be 11/4. And so there we go. Those are the values of the midpoint the value we use to plug in. And so now all we need to do is kind of combine all this stuff together. So we need to actually calculate out our area from the midpoint method. So our area is going to be sum from 1 to 6, using all 6 rectangles, of f of c sub I, so c sub I squared, since f of x is x squared, it says that above, times our width, which is 1/2. And now, just like I've done before, I'm going to factor out that width since it's common to all of them, and then I'm going to actually just square each of these things and see what we get. So 1/4 squared, just kind of in your head you can see I'm doing that, 1/4 squared, actually use a different color pen. Okay, so 1/4 squared, 1/16. 3/4 squared is 9/16. You can kind of see every one of these things is going to become over 16. That's kind of cool. 5/4 squared, 25/16. 7/4 squared is 49/16. 9/4 squared is 81/16. And 11/4 squared is 121/16. Hopefully that doesn't bug the OCD people too much that I've got a red parenthesis and a blue one, although I could pretend that never happened. Really briefly, you saw nothing. Okay, so there we go. This is expression. The sum of 6 terms in here times 1/2 is going to be the value of our rectangle. And again, I'm not a big fan of doing the arithmetic on here, although I have done all the work separately. What I end up getting as my answer is 8 and 15/16. So that 8 bugs me. Nope. Equal sign did not, but I killed it anyway. 8 and 15/16. So now, first thing I might say is that this answer sounds very reasonable to me, because our approximation here, which we self-proclaimed as better than the other two, fits neatly in between 8 and 15/16. That's very much between 6 and 7/8 and 11.375. So that's good. We definitely seem to be getting closer to it. Now though, like, you can still tell it's not there. Like, these obviously aren't little rectangles sitting on the outside that we can just like piece in. It's not like Tetris where it's like bump, 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 bump. Magically shifted over, I press the right button, and then it just fills in neatly and stacks in there, and you're like, yes, I got it. It's not quite that way. Like, it's not as exact as that. Like, these are really some sort of like curved little section here that we're looking at each time. So you can kind of tell and expect that they're not going to fill in perfectly. This can't possibly be the exact area of this function. Like, the curve is literally a curve. It's not that perfect. And we left off area here. Just something seems a little bit off about it. The question is, though, how can we actually get better? Is there a way that we can make a better approximation? Because so far, like, we've gotten closer. I would say I feel like we have gotten closer. Like, we started here with a little bit of an overestimate using rectangles on the left side. And again, we used 6 rectangles. Over here we used 6 rectangles and we used the left endpoints, and that got us a little underestimation, so we got a bound. And then we used the midpoints, so to get somewhere in between and kind of fudge it a little bit each way. And we got 8 and 15/16, which seems reasonable, but it doesn't seem like a nice, satisfying answer. Like, I feel like if this was going to be a problem that we used a whole bunch of times, like, the answer would be really, really awesome and sweet and like a whole number, because that would be a little more rewarding in this case. And checking my work, this should come out to be a whole number. So again, the question I ask you as I pause, drink water, and then check the video a little bit is, how can we make this better? How can we approximate this way and start getting closer to the exact value? Because we want the exact area underneath this curve, and I want it soon. Like, I don't want to wait too long. So think about that for a moment, and then I'll come right back. Actually, I'll probably come back faster than that, because I stopped the video and like cut it and edited it. So there we go. Think about it for a few seconds. Okay, so here we go. Like, we're ready to go and actually attack this problem. We've found some great approximations, or some solid approximations, some better than others. Specifically, the midpoint one is a little bit better than either of the other two, which both seem to have significant downsides or get significant excess or too little. But what we're ready to do is we're actually ready to find the exact area underneath the curve here. In particular, this curve is f of x equals x squared from 0 to 3. So we want to know exactly how much space is underneath there. So now up to this point, the only thing we've really changed is where those rectangles were evaluated. In the first problem, we started with stuff on the right endpoints, giving us an overestimation. So those were our right endpoints. The second one, we went on the left, and so that made things a little bit smaller. It inscribed the rectangles, gave us an underestimation. Then at the midpoints, we once again just shifted around the heights of those rectangles. Like, that's all we really did. So the one thing we haven't changed yet is we've stuck to the number of rectangles. We've stuck to 6 rectangles every time. But let's think about it for a second. We're trying to get a better approximation here. Well, why stop at 6 rectangles? What if we picked 9 rectangles? Let's think about that for a second. That would give us 3 for each of these little sections. If we did 9 rectangles, no matter which method we used, we'd go one there, one there, one there, one there. So notice what I'm doing is I'm just going, okay, let's get a few more rectangles. They're each going to be a little smaller. It'll change our width a little bit. I believe the width would be 1/3 instead of 1/2. But now what happens is notice that even when we're using right endpoints, our approximation ends up being off by less. Like, well, okay, so that last one was miserably bad. There. So now what we have is we've done the same thing. We've still overestimated it, but notice that there's a lot less space on the outside. I don't even think that's just due to my inept drawing skills either. I think that's actually part of what's happening. 9 rectangles is pretty effective. Well, I mean, shoot, if we've done 9 rectangles, why not do 30 rectangles? So instead of having 3 little ones, we'll have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll squeeze them in there, and then think about what we'll have. We'll have each of these little rectangles underneath it. And now my pen and my pixelation on my computer screen can't handle this really, but what would happen is we'd basically end up filling in this stuff, and we'd have overestimations again, or maybe underestimations, but there'd start to be less of it. We'd start to get closer and closer to the curve, because every time we take a smaller rectangle width, we can approximate that height a little closer and get a little bit more of that graph, a little more accuracy, and slowly move about it. So what you notice is this is kind of like filling up. It's like, it's getting kind of boring. In fact, drawing it, although it still looks kind of cool, although purple and green, that's like Taco Bell old colors in the 90s. And so there we could go on all the way up to 3. But what would happen is basically the thing that we can change is we can just get more rectangles. Like, why not just bring more rectangles into the thing? And in fact, to find the exact areas, that's exactly what we want, is we want to use more rectangles. But now the question comes up is, okay, well, if we're going to use more rectangles, what's the magic number? The correct answer, of course, to that would be 42. Like, 42 rectangles would be absolutely divine. Unfortunately, 42 rectangles isn't going to be quite exact enough to get us the exact area. We need more. Like, we need a ginormous number of rectangles. And in fact, look both ways, check to make sure no one's paying attention. If we just used an infinite number of rectangles, so if we had an infinity of them, what that would allow us to do is basically each of those things would be such a teensy tiny little width that we'd end up like touching the function at each one. It would almost be like our graph was just a series of rectangular lines. Like, it was just a bunch of lines. Like, it was like because it would barely be touching it. Like, they'd barely even be rectangles. And what would happen is we would end up filling in the entire thing. Okay, this is actually pretty good for eyeballing it. Like, well, now it's dying. But the point is, what we would do is if we take an infinite number of rectangles, we could squish them all together and have it fit exactly in underneath that smooth curve. We wouldn't have to worry about overestimation or underestimation because there'd just be so darn many of them, we'd be good to go. And so that's exactly what we're going to do, is we're going to get infinity of them by letting n go to infinity. And now, what's that going to look like for us? Well, it's going to change our formula. We're going to actually get an exact formula. Like, the exact area is going to come out of this. We'll still have the sum. Terrible sigma. It's still going to be our sum from 1 to n. And of course, we're changing what that n value is. It used to be 6 every time. Now it's going to be some humongous number. In particular, it's going to go all the way to infinity. We're still going to have to figure out a way to evaluate the heights and multiply by delta x sub I, which we don't know exactly yet, but we'll figure it out. The difference is, if we want to evaluate this when n gets bigger and bigger and bigger, we need to just use calculus. And in particular, we'll just take a limit. We'll say, well, hey, the exact area is equal to, actually, look at this, I got this brilliant idea. Let's see if I can do it right. Use two colors. So that's before our area formula, right? Now look at this. Wait for this. Look at this. It's a great idea. Use some holiday tones here. If we want the exact area, we need to take a limit. So we're going to let n go to infinity. We'll figure out a way to manipulate this expression a little bit more, and then we'll actually let this out. This will give us the exact area underneath the curve. And in fact, this is actually going to end up being the definition of a Riemann sum, but I'll talk about that more when I'm actually standing in front of you, as opposed to being a disembodied voice. So, that's where we're going. We want to find the exact area. We're going to do that by getting more rectangles. In particular, we're going to get an infinite number of them, so that it fits perfectly underneath it. So now, the question is, well, how do we do that? How can we reconcile our methods from before with the other rectangles using an infinite number? So that's where we're going in just 1 second. Okay, so we're trying to find the exact area here with an infinite number of rectangles. So let's see what we need. Well, let's think about it. The pieces here are still the same. We still need to find a way to evaluate the height of each of those rectangles, even if there's an infinite number of them. We still need to find what the width is. So I'm going to start with the easier of these two, and that's obviously going to be the width of the rectangles. Because even if we have an infinite number of them, no matter what, they're going to all be evenly spaced the same way. So let's think about what we said. We said that the width of the rectangle, delta x sub I, is given by taking the spread of the interval, like how far apart they are, like what that distance is, and dividing by however many rectangles we have. So number of rectangles, I'm going to abbreviate because I'm running out of gas here. 1022. Okay, so the spread divided by the number of rectangles. Well, our spread's still the same. We're still going from 0 to 3, so it's still 3 minus 0, but the number of rectangles has changed. Yes, we're going to eventually make it infinity, but let's not get ahead of ourselves. For now, we're just going to make it some n. It's a value n, so our new width is going to be 3 divided by n. When n was 6, that became 3 over 6 equals 1/2. When it was 9, like I was talking about in this example over here, it was 3 divided by 9 is 1/3, etc., etc., etc. So there we go. We do actually have one part. We've got delta x sub I. It's going to be 3 over n. So yay, we're part of the way there. And notice what we're going to do then is when we plug this into the sigma, we'll have an expression that has an n in it. So we'll be able to factor it out like a constant and work from there. So that's actually good. The width, totally cool. The height, though, that's where it's going to get a little more difficult. Like, we really have to think about how we're going to get this all spaced out. What are going to be the values? We still know that f of c sub I is just going to be whatever that partition value is squared. Like, that hasn't changed. It's still going to be that way because we still have the same function. The question is, how can we account for having this many c sub i's? I mean, before, in both of the, or all of the first three examples, we were able to find it just by looking and going, okay, well, if we've got 6 intervals, or 6 rectangles, let's just look and find what those values would be. We kind of were all hoity-toity about it, and we were able to get right there. Lovely, but not going to work here when we have an infinite number of rectangles. It'd be really hard to count them all. Instead, we have to find a way to represent where those heights are going to be. And so, I don't know if this is the exact formula people like to use, but this is how I think about it. Is we're going to figure out what our c sub i's are in terms of I. We haven't used that up to this point, but we actually want to know, okay, well, for each of those rectangles, 1, 3, 467,248, what are those values going to be? How could we find them as we split it up into more and more n's? Well, the answer is it depends on a couple things. First of all, it's going to depend a little bit on our starting point, like our interval itself, because we have to start at the left endpoint. So think about it this way. 0 to 3 is our a comma b, and so we're going to start over here. That's going to be where our first rectangle would begin, is at that first point. So we start there. So that's going to always be our first point, is that'll just be our left endpoint. Like, that will be our first, the value that starts our c sub I. And this is going to be a formula for it. We'll actually write out the specific one in a second. Next, we've got to add on where all the next ones will be. And remember, they're always delta x sub I away. We said in our first example, all the way at the beginning, that we found our first endpoint. It was at 1/2, and then we added a width to get our next one. 1/2 plus 1/2 is 1. 1 plus 1/2 is 3/2. 3/2 plus 1/2 is 2, and so on and so forth. So over here, that's the exact same thing we want to do. we want to take that first, that left point, endpoint, that first place we're going to start calculating out the rectangles and finding their heights, and we're going to add in the width. So we're going to add in delta x sub I, because that's going to allow us to go from the first endpoint, the first point we have, to our next point. If delta x sub I is 1/2, we start at 0, we go 1/2, then we add it again and again and again. So from there, the only thing we need to add on is, in addition to our delta x sub I, we then have to multiply by I. Like this is a plus delta x sub I times I, because I will allow us to account for each of the different places we're going to evaluate it. We'll evaluate it at the first place, then the second place, then the third place, and then the fourth place, then the fifth place, all the way up to whatever that n value happens to be. In our particular case, we're just going to go all the way up to n and then evaluate it as a limit. And so there we go. This is going to be our formula. So we've got, I already said the left endpoint, then it's going to be the width, and then it's going to be the counter, so I. What is this? The index of summation. And so this will be our method for finding those partition values. Sorry, terrible box. Sorry. So now, as far as our particular example, like we actually need to look at what we know. So to find our c sub I here, I should probably write that. And this is a little confusing, but again, as I said, I'm on my last wind. So our c sub I here, well, let's look at our pieces. Our a value here, our first place that we start looking or start evaluating this sum or this area, is at 0. So we're going to start at 0, our a value, then we're going to add delta x sub I. Well, delta x sub I is right there. It's 3 over n. So we'll go 3 over n, and then times our index of summation. So our c sub i's are going to be given by 3 over n times I. So now, just as kind of a point, this is great, like this is useful. We're only a couple steps away in some algebra away from getting to our answer. But now let's think about this. So I said this is how you can find those values. Does this actually match what we did before? 3 over n times I. Well, let's look up here. So if we want to find the partitions here, I said those were our partition values right there. Well, does that work? So 3 over n times I. Because this is the same situation. We're still trying to find the area underneath x squared from 0 to 3. Well, if we do that, we said n was 6. So that means this is 3 over 6 times I, or 1/2 times I. Then from here, if we're summing from 1 to 6, so we said we're going from 1 to 6, that means we'll have 1/2 times 1 is 1/2, plus 1/2 times 2 is 1, plus 1/2 times 3 is 3/2, 1/2 times 4 is 2, 1/2 times 5 is 5/2, and 1/2 times 3 is, wait, what did I screw up? Did I screw up something? 4, 5, 6, yeah, is 3. And so there we go. Notice that they're the exact same 6 values that we got before. So in fact, this method that we used is actually just a generalization of what we used in the past. Not huge, again, it's very straightforward to get out of this formula, but there we go. So from here, we have found now the width of the rectangle, and we found the values that we're going to evaluate the heights at for all of these rectangles. So from here, what else can we do? Well, I might notice that since I've got c sub I, since this is c sub I, that means that our value of our function f of c sub I is going to be that thing squared. It's going to be 3 over n times I squared, because our function is x squared. That, of course, simplifies to 9 over n squared times I squared. And so this guy is going to literally go into our sum formula, just like our width will here. Okay, like if this was a regular class, I would go questions. Then I would stare out at the class, very closely paying attention, looking for movements, subtle signs of a shoulder flexing or a hand moving into the air, and then nobody would do anything or move a muscle or even blink an eye. So instead of having to do that now, I can just narrate it and move on. So questions? Too bad now you can't ask any. Wish you'd asked questions before. Maybe I would have stuck around. So anyway, here we go. We found some pieces. We found an expression for the width of the rectangles when we have n of them instead of having a specific number, and we found an expression for the height too, using all this information. So now here we go. Let's throw it in. We want to find the limit as n goes to infinity of the sum from 1 to n of f of c sub I times delta x sub I. Well, from here, I'm going to stop writing limit as n goes to infinity every time just because that gets kind of tiring. So I'm going to draw an arrow to say that we're using the same thing. It's just like we're saying it's equal to without the limit. So I'm going to do the sum from 1 to n of f of c sub I, that's c sub I squared, which comes out to be 9 over n squared I squared, times my width, which is 3 over n. So there are my two pieces. Here is f of c sub I. Here is delta x sub I. There are all my pieces. My only job now from here is to simplify all this, use all the rules that I know for sigmas, and then come out and evaluate a limit at the very last step. So let's go ahead and start that. So from here, what can I do to simplify it? Well, I've already got it simplified in here. I've plugged it straight in. So from here, I just need to actually bring out any of the constants. And I'll notice that I have a constant right there, 9 over n squared, and I have a constant right here, 3 over n. If I multiply those guys together, like it says to do right here, that means I'm going to have 27 over n cubed as a constant. So I'm going to pull that whole thing out, and I'll leave myself with whatever's left, which in particular says the sum from 1 to n of I squared. And so this is what we're left to evaluate. And now what's nice is notice this guy, this beast, is something that we actually looked at yesterday. Like it's actually sitting on the first page of your little packet thingy that you probably have in front of you if you're doing what you're supposed to. This guy actually is something that we know. This thing can actually be rewritten as 27 over n cubed times 3 terms being added together, because I'm going to use the simpler version, the version I like that has the 3 separate fractions. In particular, the sum from 1 to n of I squared is n cubed over 3 plus n squared over 2 plus n over 6. And so there it is. My answer is like almost there. So from here, what do I got to do? It's a matter of distributing. So I'm just going to distribute into each of those little guys. That's going to give me first, I'll have 27 n cubed over 3n cubed. I'm actually going to write it out because otherwise I tend to go too fast. Next one is going to be 27 n squared over 2n cubed. And lastly, it's going to be 27n over 6n cubed. And that is going to simplify to then. So again, I've just distributed in. I'm just going to simplify it then a little bit. It's going to simplify to 9 plus 27 over 2n plus 9 over 2n squared. And so there we go. That's the expression that comes out of the summation. Like this whole thing is actually equal to this. But that's not all that we want to do. We actually want to go further. We want to get the exact area underneath the curve. So to do that, we take the limit. We just say that, okay, we've got an expression in terms of n. We want to see what happens as we pick bigger and bigger values of n. So what happens if we pick so many rectangles that it actually filled in and made everything fit perfectly? Well, that just simply says the limit as n goes to infinity of this guy. And now what's nice is one of these pieces is going to just stick around. Limit as n goes to infinity of 9 is still 9. Over here though, once you have 27 over infinity, 27 over a gigantically humongous number, this goes to 0. So does this one because it's also over n. That means that our answer is just 9. So the exact area under the curve, according to this method, looks to be exactly 9. So now, that's a little more rewarding. I like the answer of 9. And let's think about this. We said that the exact area had to be between our upper and lower bound, and that the midpoint ones seemed to be close. Well, look right here. 6 and 7/8 is less than the area, is less than 11 and 3/8. The area, if the exact area is really 9, 9 would fit beautifully right in the middle. And in fact, 8 and 15/16 is ridiculously close to the actual answer. So the midpoint method was really effective, just not perfect. And so there we go. What we've done is we've now actually found the exact area using calculus in tandem with some of the summation stuff and our analysis based on rectangles. We started with this idea of calculating out the area by summing up a whole bunch of rectangle areas. We found the width by comparing the width of the interval to the number of rectangles we had to get an expression here. That was kind of our first important part. Then our next important part was to figure out how we could evaluate the height at each of those infinite number of rectangles. And we did that right here. We figured out that it had to start with our first place, like the left side of our interval, and then we had to add in the width each time a bunch of number of times to get our value. From there, to actually find the heights, we plugged that partition value into the actual function, which was x squared, and got out an expression that allowed us to plug it straight into the intervals, or into the summation formula right here we had for area, work through it using some of our summation formulas, and then at the very end, take our expression in terms of n and evaluate the limit as n goes to infinity, and give us the exact area underneath the curve. Just as though we'd had an infinite number of really thin rectangles that filled in the whole area underneath it. And so there we go. This is a pretty cool thing. It's a process, if I remember right, I believe what we're doing is we're finding the Riemann sum of the rectangles underneath the curve there of x squared. So now, our next step is just like, can we verify this? Does this actually make sense? Like, does it look this way? And so I'm going to actually pull up that Java applet in just a second and have us take a look at it. Okay, before we move on, as I said, I just want to see if this actually matches what we expected. Like, is this going to actually match our intuit, or the answer we just found? Like, if we pick more and more rectangles, will this actually give us the answer of 9, which is what what the last example indicated. So from here, I'm going to go through and do just like I did before. I'll set it up so that we have our normal picture. And so there we go. Here is our function. It's x squared. Right now it says there's 2 rectangles, and so what we want to do is, let's first switch it to, I don't know, left endpoints. You know what, let's even go right endpoints. Those are kind of cool. I like seeing right endpoints. And so now our question is, well, like, did our answer work out? We said over here that if we take more and more rectangles, our answer should eventually get to 9. Like, the answer is approaching 9 at an infinite number of rectangles. So let's see. 2 is kind of a small number. We did 6 before. Remember, we got 11 and 3/8, so 6 is good. One number bigger than 6. Let's go 15. If we use 15 rectangles, notice that our area ends up as 9.92. Like, that's getting fairly close. What if we went to 25 rectangles? 9.54, got a little better. What about, dare I go, 42 rectangles? Notice it's getting a little smaller. Notice delta x sub I, that distance between the 8 rectangles is getting smaller and smaller. And again, this is like totally awesome for seeing what's happening here. Let's just up it a little bit. Go 100 rectangles. So blue area, total blue area, 9.13. Well, I'll take your 100 and raise you 1,000. Oh, look at that. It's basically just like a solid rectangle stuff. Pretty darn cool, and pretty darn close to 9. I haven't really experimented with this, but what if I go 1... No, I was going to go 1 million, but just so I could use the Dr. Evil voice. Let's go 10,000. So notice it didn't even change up here. The delta is down to some tiny number, and the blue area, 9 to 2 decimal places. Let's just go once more. Let's go 1 million. Let's just see if it even goes. I don't know if it will. It might like freeze my computer. Hopefully not. It's not happy about doing it. In fact, it's kind of like shaking at me, but that's okay, because we don't actually need to. Like, I think this has pretty much confirmed what we would expect. Went through this whole process. We said that as we pick more and more rectangles, the answer goes to 9, and in fact here we're seeing that it does in fact go to 9. With 2 rectangles, not 9. With 42 rectangles, closer to 9. With 10,000 rectangles, or even 1,000 rectangles, very close to 9, to the point where I feel like we're safe in saying it's definitely 9. So at least again, according to this random applet I pulled up and told you works, it looks like we did everything correctly. So very nice. Okay, so then what do we have left to do? Well, my voice is killing me and I'm exhausted, but I want to do one more problem. I want to do number 7, just so you once again see the process for setting up the what's going to be called the Riemann sum tomorrow, like to find the area under the curve exactly, without overestimating or underestimating in any way. So to do that, first I want to see if I got the right color pen. Hey, red's okay. I'm cool with red. We're going to look at the problem in a little bit different fashion. We're going to look and find the exact area of the region bounded by the graph of y equals x squared, so same graph, but this time we're going to use a different interval. We're going to use the interval 1 to 3. So we just want to find what is the exact area between here and here. So it almost looks like kind of a trapezoidal region type thing. So we want to know how much area is contained under here. Like, what is it come out to be? It's actually fun to color things. I really enjoyed coloring when I was a kid. I still actually do, but don't have a whole lot of opportunities for it. Okay, so we want to find the exact area underneath there. Process is going to be exactly the same as right here. We're just going to have to adjust for that little change that happens when our interval changes. So in fact, obviously too, you could think to yourself, well, what am I going to know? How will I know if this answer makes sense? Well, the answer should be smaller than the one before in the last example, because we're only going from 1 to 3. So there's less area here. We've taken off that little bit. Okay, so what do we got? Well, our exact area is going to be equal to the limit as n goes to infinity, to account for the fact that we're going to take an infinite number of rectangles here to get exactly our answer, of the sum from 1 to n of f of c sub I, so the heights of all those rectangles, times the width of each one, based on what we have. And so now again, we'll start at the same place. Let's find the width. So will the width of these rectangles change? Well, the answer is yes, it should. When we take the spread over the number of rectangles, we have changed our spread. Why? That's a rectangle. Spread over number of rectangles. That has changed. No longer is it from 0 to 3. It's now from 3 to 1. So our spread is just going to be 3 minus 1, or 2. And there's still going to be n rectangles, because we're trying to be able to go up to a really big number. So our new width is going to be 2 over n. So that will in fact change our answer. So we already have like our first step. Like, we're not going to have the exact same thing as before. Next, the height of those rectangles. The most critical part, and the place where it's easiest to get confused. Our height is going to be based on the function value of c sub I, which will still be c sub I squared. The difference is now we're going to have to find new c sub i's. So I will start by writing out what our c sub I formula is, or like the process for finding it. It's basically the first part, like the left endpoint of our interval, plus the width times our index of summation, so that we can get one height for each of the n rectangles that we deal with. Over here then, like what we've got is we now have this extra piece. Like, we're going from A to B, so A has changed. It's not 0 like before, it's actually 1. So our c sub I is going to be 1 plus delta x sub I, so our width of 2 over n, times our index of summation. And so this is now c sub I. So there's a little more complicated. Like, we're actually plugging in something a little more dramatic into our function than we did before. So what will that look like? Well, f of c sub I is going to be this thing squared, which is going to FOIL out. Like, I will actually just go ahead and use FOIL. I'll do it in my head though. We're going to get, I'm going to reverse the order if that's okay. I'm going to just kind of pretend this one is first. We're going to get 4 over n squared times I squared, plus 4 over n times I, plus 1 squared, which is 1. So this guy represents f of c sub I. So we've got our expression for the width, we've got our expression for the heights. Now we're ready to go through and do the summation. And again, all we're doing is we're using what we know about how the width is calculated and how we can figure out where those heights and stuff are going to be on the rectangles. Oops. So let's see. Pen settings. Let's get a more epic color, like black, classic black. So here we go. So we want to go through, want to calculate our area. Again, we're going to do the limit at the last step, but I'll write it here so that we don't forget it, because we want to get an exact area of the sum from 1 to n, f of c sub I times delta x sub I. Okay, so this is going to be the most epic algebraic work here. In fact, kind of on a tangent, like a lot of people actually say that the hardest part of calculus is the algebra. Like the concept, like you can get this, you can draw a picture, you can shade stuff and color stuff, like you feel really good about yourself. Sometimes though it really is difficult to just kind of get a handle on the rigorous demands of the actual algebra work and the computation you have to go through. And this is one of those examples. So from here, we want to find this area. We are going to take the sum from 1 to n of f of c sub I. It's going to be 4 over n squared, I squared. I'm literally just taking this guy right here and bring it down. Plus 4 over n times I plus 1. Then I'm going to multiply all of that times the width, which is 2 over n. So from here, it's just going to be a mad dash of algebra. And again, my throat's starting to kill me from doing this. I don't know why it sounds so uncomfortable. But as we go through here, I'm going to bring this guy out in front. So I'm going to do 2 over n times, and then I'm going to have a whole bunch of individual summations. And for each of those summations, I'm going to also factor out the constant sitting there. And then I'll reconcile everything at the very end. You know what? Actually, that's going to be really annoying. So why don't I do this? I'm going to distribute this in right off the bat. Did that first, just because that'll save me some space. And then we'll go through and start working from there. So distribute it in. I'm going to have the sum from 1 to n of 8 over n cubed times I squared plus 8 over n squared times I plus just plain old 2 over n. So there's my summation that I'm going to be working with. Now for each of these, I'm going to turn it into an individual summation so I can start working through it. So factoring out the constant, the first one's going to be 8 over n cubed times the sum from 1 to n of I squared. And again, the sum from 1 to n of I squared, we know, that's a formula. Plus 8 over n squared times the sum from 1 to n of I plus 2 over n times the sum from 1 to n of just plain old 1. Like there's nothing else left. And so this will yield, if we use the appropriate formulas for this, and this, what we're looking for. So next step, let's actually apply those formulas. We know each of them. So the first part, 8 over n cubed. The sum from 1 to n of I squared is n cubed over 3 plus n squared over 2 plus n over 6. The next one, so 8 over n squared times the sum from 1 to n of I is going to be n times n plus 1 over 2, or n squared over 2 plus n over 2. Then lastly, the sum from 1 to n of 1 is just going to be n. So 2 over n times n. And so there it is. We're almost there. We're like cutting off one simplifying step each and every time to try to get us closer and closer to this answer. So moving on. I feel like I'm going to make a mistake at some point here just because it's gone well up to this point, or my computer will crash or the power will go out. So I should probably stop talking about jinxes and actually work. Okay, so from here, I'm going to do the distributing work. So the first one is going to be 8n cubed over 3n cubed. That's going to become 8 over 3. So notice I'm going to save myself a little bit of time by doing some of these multiplications as I go. The next one, 8 over n cubed times n squared over 2 is 8n squared over 2n cubed. So that's going to be 4 over n. Plus the next one will be 4 over 3n cubed. I think I did that right. No, it'd be n squared, sorry. So see, I'm starting to doubt myself. Okay, so there's my first 3 terms taken care of. Next ones, it'll be 4, because 8n squared over 2n squared, plus 4 over n. Last one, 2 over n times n is just 2. And so here we go. We're really close to our answer. All that's left is we want to, instead of just leaving it like that in terms of n, we want to say, well, what happens when we pick an infinite number for n? What happens as we take n to infinity? So we want to do the limit as n goes to infinity of this guy. So now the question is, have I done it correctly? I think I'm okay. Okay, so from here, as the limit as n goes to infinity, well, anything with an n, the denominator is going to become 4 over gigantic, or it's going to be a number over a gigantic number. It's just going to go to 0. So that guy goes to 0. He goes to 0. Goodbye, you went to 0 too. There we go. So what we're left with is 8 over 3 plus 4 plus 2, so plus 6, if I do a nice little common denominator to feel good about myself, that's going to give me 8 over 3 plus 18 over 3 is going to be 26 over 3, which is the same thing as 8 2/3. So there we go. Our answer appears to be exactly 8 2/3. Now, we could go and check this on the thing and see if it actually looks about right. And you know what, why the heck not? Let's do that. Okay, so I said we're going to check. There it is. If you wonder why there's that weird break, it's because I had to check the video and make everything so it doesn't get erased or anything. Okay, so here we go. We said after doing this work that the area underneath the curve formed by y equals x squared in the x-axis between 0 and 3 was 9. And from here, we went and found out that the area between 1 and 3, so cutting off that little other end here, is 8 2/3. So the question is, does this actually fit here? Tomorrow in class, tomorrow being Friday, I'll show you a way to do this on the calculator and actually have it show a cool little picture where it shows the infinite number of rectangles and then tells you the actual value, the exact value. For now, though, I'm just going to keep using this applet because I already have it up and I'm ready to go to sleep. So first of all, we said this is what happens when you pick a whole bunch of intervals. So right there I picked one interval, and it just gave me my one little rectangle. If I went back to my 6, it says the blue area is about 10.037. So like it's starting to get close there. Or it's on the right track. So from there normally we go 25. It says 8.988. 42. Starting to get down there. Remember, 8 2/3 is just 8.66666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666 Up it. 100. Reasonable. 1,000. Oh, there we got 8.67. And 10,000. 8.668. So now beyond here, obviously the applet gets confused, but notice there's a beautiful little rendition. It's with all those rectangles in there, it's all but filled it in, and our value is definitely getting really close to 8 2/3. So I feel safe in saying, especially because I did all the work, that our calculation is correct. We did find the correct area underneath the curve using this limit process that's built from here. And so, in fact, like I know there's another page on your work here, but nothing on there is necessary for doing the homework assignment that I have assigned for tonight. Most of everything on there is review of what we did on Tuesday as well as what we did yesterday. So I'm going to go ahead and leave that last page to work on a little bit on Friday. I'm going to have it all worked out. I'll figure out a way to kind of go through it. It's just kind of the same practice, a little more work with everything. Maybe I'll let you guys work on it. But anyway, just to kind of, before I go and cut this off and let you finish, let's just kind of review what we did today in the last couple days. Basically, we were trying to find the area underneath the curve for whatever reason it was. We did that by calculating the area of rectangles that approximated the area. We started out with rectangles on using the right side. We got an overestimation. From there we went and did on the left, we got an underestimation. So we're kind of swinging back and forth between getting what we wanted. We want to get as close as possible. When we used midpoints, it felt better. It was definitely in between, and we could see that some of the like excess areas and missing area were kind of filling each other in. So it seemed like we were getting closer. Not exact though. To find the exact angle or the exact area underneath the curve, we needed more cowbell. We needed more rectangles. Like we needed to use more rectangles so we could start filling it in, as my little pictures over here showed. And so to do that, we took the limit as n went to infinity of that same formula, and then we had to just be a little more careful. We had to interpret our width in terms of n instead of a specific value like 6, and we had to find a way to calculate or find an expression that represented where those heights are going to be taken for each of the rectangles. And we did that here. Once we did that, it was just a matter of plugging in and using all the summation stuff that we already knew from before. Like plugging in, using the formulas, and then simplifying and being really algebraically careful here. Because there really are lots of places to make an algebraic mistake. Finally, we did it again using a different interval, a shorter one just to confirm if everything worked. The algebraic burden was even higher. We had way more stuff to deal with because we had a binomial here that had to multiply out. But when it threw it, there was nothing really new otherwise. It was just a little bit more work, a little bit more multiplying, a little bit more formulas. And when we went through, we were able to find that area as well. So at this point, I feel like I'm safe in saying that I've more than taken care of this off day. So hopefully you guys have gotten a solid grasp, so far at least, based on this limited exposure, to how we can find the area underneath the curve and how we can better and better approximate it, and then eventually use calculus to get to the exact area. And we'll continue working on it on Friday in class as well, and going forward the next week or so with different applications and stuff. So at this point, at 11:01 p.m., still need to put together the DVD and burn all this and edit it. This is Mr. Steele signing off. Hope everyone has a good rest of your day, or had a good day. I will see you tomorrow. Have a good night, or afternoon.